Section 5.4 is going to give us a little bit of a break from the unit circle stuff, and we're going to be working with just solving right triangles and some applications. To solve a right triangle means that you're going to find the measures of all angles and all sides of the triangle. All of the triangles that we work with in section 5.4 are going to be right triangles. We'll use a lowercase a to represent the side opposite from angle A. So here, like if this is angle A, side A is here. The length of the side opposite angle B is side B, so lowercase b is the side opposite from the angle B. And lowercase c represents the hypotenuse, and of course capital C is going to be the 90-degree angle. In example 1, we're going to solve the right triangle ABC. If angle A is 34 degrees 30 minutes and side C, or the hypotenuse, is 12.7 inches. Alright, so what can we do with this? Oh, I'm sorry, I just went off the screen for you. There you go. So what can we do? Look at what we've given. We've got a calculation for angle A, and let's convert this into decimal degrees instead of degrees and minutes. And then when we get finished, we can convert it back because it'll be easier. Most of us probably prefer to work with decimal degrees. So we've got angle A, 34 degrees, 30 minutes. That's the same as, you know that there are 60 minutes in a degree, so that's 34 plus 30 over 60, and that gives us 34.5 degrees. So we can use 34.5 for angle A. And then to find the others, go look at the illustration. Suppose I want to find side length B. I've got a value for angle A and I've got a value for my hypotenuse, so thinking about opposite and adjacent and hypotenuse values, if I'm here and I'm going to solve for side B is adjacent to angle A. So which trig function can I use that involves adjacent over hypotenuse? That would be cosine. So I can do cosine of angle A, or 34.5. I know that cosine is equal to opposite over I know that cosine is equal to opposite over hypotenuse. I'm sorry. Cosine is adjacent over hypotenuse. So I'm going to do cosine 34.5. This is adjacent over hypotenuse. Okay? My adjacent side is going to be side B, and my hypotenuse is 12.7. Okay, so I'm going to solve cosine 34.5 equals B over 12.7. I can multiply both sides by 12.7. So 12.7 times cosine 34.5 equals B. And type that into the calculator. And we are still working in degrees, so make sure your calculator is set to degrees. Alright, so we're going to do 12.7 times cosine 34.5. And that gives me 10.4664 for side B. I'm going to call it 10.5. So 10.5 is side B. So that means this side has length 10.5. I believe these are in inches. Alright, we can get side A two different ways. You could use the Pythagorean theorem if you wanted with the value that you just got, but I personally prefer to try to use as much original information as possible when I'm working through the problem. In case I make a mistake, I don't want to build on that and make more mistakes. So I'm going to find side A, and I'm going to still use angle A. Side A is opposite from angle A, and I'm going to use my hypotenuse 12.7. So which trig function will apply? If I'm doing opposite over hypotenuse, that's sine. So I'm going to do sine of 34.5 equals opposite, so side A, over the hypotenuse 12.7. Multiply both sides by 12.7. 12.7 times sine 34.5. And then we'll see what that gives us. So 12.7 times sine of 34.5. That gives me 7.1933599209. So about 7.2. Okay. And as far as finding angle B, you can do it using your trig functions, but you can also just use it using basic geometry knowledge. You know that your triangle has 180 degrees total, and we know that this is 90 degrees and this is 34.5 degrees, so we can just subtract. We know that 180 for the entire triangle minus the 90 degree angle minus 34.5 from angle A leaves us with 55.5 for angle B. So angle B is 55.5 degrees. And then we'll just convert that back into degrees, minutes, seconds form. Okay, so 34.5 degrees, you're going to multiply the 5 by 60, multiply your 0.5 by 60, that's going to give you 30 minutes. Okay, so I've done all of my work, I've just got to write it so it's easy to locate. So angle A, what was given to us, angle B is 55 degrees, 30 minutes, because you just multiply 0.5 by 60. Excuse me. Alright, so finishing up, we've done the work, we're just giving our answers now. We found that angle B is 55 degrees, 30 minutes. Side A was approximately 7.2 inches. And side B was 10.5 inches. Okay, so we now have all the angles and all of the sides. Let's look at example 2. We want to solve right triangle ABC if side A is 29.43 centimeters and the hypotenuse is 53.58 centimeters. So they didn't give us any angles, except that we do know we have a right triangle. So we have a 90 degree angle. We should be able to get the rest. Okay, so we've got side A is 29.43. Side B, oops, I didn't mean to do that. That's okay. The hypotenuse is 53.58 centimeters. And that's all they gave us. This is angle A and this is angle B because they're opposite from those corresponding sides. So we're given a hypotenuse and we're giving one of the sides. So let's say if I were to start with angle B, I'm given a value for my adjacent side and I've got a value for my hypotenuse. So if I can do adjacent over hypotenuse, that would be my cosine function. So I can do cosine B equals adjacent 29.43 over the hypotenuse 53.58. How do I solve that for B? Well, because you've got B inside your cosine function, you got to get it out of there. So to get B out of the cosine function, let's apply cosine inverse to both sides. So that's going to give me B equal cosine inverse of all this, 29.43 over 53.58. And we'll type that into our calculator and see what we get. So you're going to go second cosine, and then in parentheses you're going to do 29.43 divided by 53.58. That gives me 56.68. I'm just going to stop there. It keeps going, but I'm going to say angle B is 56.68. Now, angle A, we could get the same way, or we can just subtract what we just got from 90 degrees and figure out angle A as well. But like I said in the previous example, I like to use as much of my original information as possible. So I'm going to find angle A, and this time I'm doing opposite over hypotenuse, so I'm going to use the sine function. So I'm going to do sine A equals 29.43 over 53.58. Remember, sine A is the opposite over the hypotenuse. And then I can take sine inverse, and I'll have A equals sine inverse 29.43 over 53.58, and type that in and see what that gives us. So second sine gives me sine inverse 29.43 divided by 53.58, close parentheses. Make sure you close the parentheses. It could make a difference in your answer. I'm getting 33.3. That's an approximation, but that's okay. 33.3. These are in degrees. All right, so I'm going to go ahead and box those in. That's part of my answer. That's part of my answer. And I'm sorry, that's what it looks like. Okay, what's left? What else do I need to solve? I need to get side B. So I can find side B. You can use your trig functions if you want to, or you can, because you were given the hypotenuse and you were given side A, I would go to the Pythagorean theorem here. That's one way you could do it. If you use your trig functions if you use your trig functions to find this remaining side, you're going to have to use some material that you calculated on your own. And in order to stick with the given information as much as possible, we'll do, I'm going to do the Pythagorean theorem. So the Pythagorean theorem tells me that b squared plus a squared equals my hypotenuse square, 53.58 square. And I'm sorry, I could have put my 29.43 in for a, but so b squared plus 29.43 square equals our hypotenuse square, 53.58 square. So if you want to be really organized about it, you can write c square there. And then we'll do these calculations. So we'll have b squared equals, and we're going to subtract, so we'll have 53.58 square minus 29.43 square. And then b is the square root of all that. So b equals, or we can just calculate it first if you want. 53.58 square minus 29.43 square. That's giving me 2004.6915. And then when you take your square root, we get 44.77 for side B. And that unit is centimeters. Okay, and that's it for example 2. The next thing we're talking about is angles of elevation or depression. So, let's read it first and then I will explain what it means. In applications of right triangles, the angle of elevation from point X to point Y is the acute angle formed by ray XY, which hopefully you can see, ray XY, and a horizontal ray within point X. So angle of elevation is also there are two types of angles that we're working with: angles of elevation and angles of depression. They're both based on what we call line of sight. So imagine if you are, let's say we've got someone standing here, and I'm not a good artist, but I'm going to try to draw it. So that's his face, all right, and then here's his body. And he's looking off to the side here, okay? So he's looking off to the side, and then here's his feet. All right, so here's his eyes. If he's looking up like this, and this is his line of sight, this is what we call angle of elevation. Okay, it's based on his line of sight. So if he's having to look up, then we have an angle of elevation. If he's having to look down, which I'll do that in a different color, so this is the angle of elevation. If he's having to look down, this one is called angle of depression. Okay. So that's what that means. So it's all based on your line of sight as you look across. If you're looking up at the sky, you'll have an angle of elevation from your line of sight. If you're looking down into maybe into a canyon, you'll have an angle of depression from your line of sight. So the angle of depression from point X to point Y is the acute angle formed by ray XY and a horizontal ray within point X. So you can see we've drawn a horizontal and we've got an angle of depression, and you can think of this person as standing up here, and he's looking, having to look down. Okay, so and there's his eyes. So I know that's a horrible drawing, but hopefully it's clear what is going on here. Here's his line of sight. He's looking down, so it's an angle of depression. Example 3. Pat Porterfield knows that when she stands 123 feet from the base of a flagpole, the angle of elevation to the top of the flagpole was 26 degrees 40 minutes. If her eyes are 5.3 feet above the ground, find the height of the flagpole. So we need to draw a picture. We're going to be drawing lots of pictures in this section. For every one of these application problems, we need a picture to go with it. So we're going to draw Pat. So let's draw the ground, and we'll draw Pat standing on the ground. I'm just going to draw a stick figure now. But this is her line of sight this way. And there's a flagpole over here. So I'll draw it, and here's my flag. Okay, here's her line of sight, but if she looks up at the flagpole, we create an angle of elevation from her line of sight. This is the angle of elevation. Now, what do they tell us about this? Her eyes are 5.3 feet above the ground, so that means the distance from here to here is 5.3 feet. Okay, that's the ground, and that's how tall she is. She's standing 123 feet from the base of the flagpole. So this is 123 feet here. Her angle of elevation that's formed by looking up at the flagpole is this 26 degrees 40 minutes. 26 degrees 40 minutes. And we are asked to find the height of the flagpole. So we need to find X over here, which is from her line of sight to the top of the flagpole. And of course, once we find that, we'll also need to add in the 5.3 feet from her eyes to the ground. So we've got a right angle formed here, and we've got a hypotenuse here. We're solving this for X. And I noticed that my angle is in degrees and minutes. You can type it into the calculator like that if you want to. It's not, if you've got the TI-84, it's easy to type it in that way, so I may just keep it that way, and I'll show you how I type it in. How are we going to find X? We don't have a value for our hypotenuse. We have a value for this base down here. So from her line of sight, the 123 feet would be an adjacent side to this angle theta, and X would be the opposite side. So we could use, which function can we use if we're using adjacent and opposite? That's going to be the tangent function. So let's calculate tan of 26 degrees 40 minutes we know that this is equal to opposite x over adjacent 123. And then if I multiply both sides of my equation by 123, I've got 123 times tan of 26 degrees 40 minutes equals x. And we'll type that into the calculator. Okay, so how are we going to type this in? I'm going to type in, let's do the degree part first. We're going to do tan 26, and then this is degrees. So I need to go to angle, my angle menu, which is in you'll access by going second apps, and then you've got degrees and minutes. So I'm going to select 1 for degrees, and then I need to type 40 and go back to second apps and select 2 to get it into for the minutes and close parentheses. So it's all so this is so I'm asking the calculator to tell me tan of 26 degrees 40 minutes, and enter, and then multiply that number by the 123. That gives me 61.77 for x. Okay, so putting the 61.77 over here for x, we can find the height of the flagpole if we just add the 5.3 feet to the 61.77. So 61.77 plus 5.3 is going to give us 67.07. And this, I believe, was in feet. So the flagpole was 67.07 feet tall. Okay, so that's example 3. That's how angle of elevation is computed or calculated. Example 4, we get to work with angle of depression, and we've already got our picture this time. From the top of a 210-foot cliff, so I've drawn a cliff over here. This is my cliff. That's supposed to be grass, and then that's the edge of the cliff, and then I've got water down here. So this is a cliff. From the top of a 210-foot cliff, David observes. So we've got David standing up here. He observes a lighthouse that is 430 feet offshore. Okay, so it's way out here, 430 feet away from the shore. Find the angle of depression from the top of the cliff to the base of the lighthouse over here. So remember, his line of sight, the angle of depression is measured from his line of sight. I should have drawn this a little bit better where I had, because I didn't in my picture I didn't account for David's height, but that's okay. We're going from where his eyes should be over here, so maybe I should draw him like this. Here's his eyes. Here's his line of sight here. We want to find the angle of depression that's formed from him looking down to the lighthouse. So that's the angle that we need. So we'll call that theta. And to get this, we've got a right triangle here. We've got one side to work with. Excuse me, we've got two sides, 210 and 430. We've got two sides to work with, so we can use those two sides. I'm going to call this angle theta prime, and then when I subtract it from 90, it's going to give me my theta. Okay, so starting with what we're given, we're trying to find, if we can find the measure of theta prime, we can find this by doing 210 feet is the adjacent side, and then 430 feet is going to be my opposite side. So adjacent and opposite, that's tangent again. So I can do tan of theta prime equals my opposite side 430 over my adjacent side 210. And then I can solve for this angle if I take the inverse function, tan inverse on both sides. So I get theta prime equals tan inverse 430 over 210. And I'm sorry, that's what I have. Okay, so I did tangent of theta prime is opposite over adjacent. So 430 over 210. And then to get my theta prime, I need to do the tan inverse function on both sides. So that gives me this. This can be typed into my calculator. I can get my decimal approximation. So we're going to do second tan to get to the tan inverse function. And we'll type in 430 over 210, close parentheses. And we get 63.97 for theta prime. So that means that the inside angle is 63.97. The angle of depression is the angle that's measured from his line of sight over here. So I can get this if I just subtract it from 90 degrees because the two together create a 90-degree angle here. So if I do 90 minus 63.97, that gives me an angle of 26.03. So I'm going to say it's approximately 26 degrees. And that is my angle of depression, approximately 26 degrees. And that's example 4. I'm sorry, there it is. That was my work at the end. Okay, then we have other applications of right triangles. Alright, so another application involves bearing. And bearing is an important concept in navigation. There are two methods for expressing bearing. Method 1 states that when a single angle is given, it is understood that the bearing is measured in a clockwise direction from due north. So we're just going to draw these different angles using bearing. So draw it in example 5, we want to draw a bearing of 32 degrees, 164 degrees, 229 degrees, and 304 degrees. So the way this works is you're working from, let's see, it said the bearing is measured in a clockwise direction from due north. So you're going to start with a point and so to draw a bearing of 32 degrees, we start at a point, this is due north, so we're going to go straight down. And then we're going to measure an angle of 32 degrees from this vertical line. So 32 degrees is going to be a small sliver, about a third of a 90-degree angle, like this. So that's 32 degrees. Part B, we want an angle of 164 degrees. So again, we start due north, we go vertically down, and then from here we're going to measure 164 degrees. So starting here, we're always going clockwise in these problems. So starting from here, we want to go around. So we're rotating from this point. So rotating from here. So let's say you're starting like this, and then you're going to go around until you've moved 164 degrees. So once I get here, I've traveled 90 degrees. And when I come down here, I've done 180. So I'm in somewhere in this area is 164, like this. So this is just, I mean, it's not, you don't have to draw this perfectly, obviously. It's just to help you understand where everything needs to go so you can see it visually. In part C, we want a bearing of 229 degrees. So again, we start due north and we're going to draw a vertical piece, or one side of our angle is going to be this vertical line from due north. And then from here, we're going to rotate 229 degrees from there. So we're going to go, this is 90 degrees, this is 180 degrees, and then if we went up, if we got this far, we would have 270. That would be too far. So we're going to be somewhere in here, between 180 and 270, like this. And our angle was measured all the way around this way. That's 229 degrees. In part D, 304 degrees, we start due north, draw a vertical line, and then from that vertical line we want to measure 304 degrees. I'm going to turn around this way, that'll be better. So this is going to get me, there's 90 degrees, that's 180 degrees, that's 270 degrees, and then I know all the way back up would be 360, so I'm somewhere in this area now. So it's like this. So 304 would look like that. Okay, so that's how we will draw a bearing when only one angle is given. It's always going to start with that vertical line at due north, and then we will rotate from the bottom, from the vertex. The vertex will be down here each time, and we'll rotate from that vertex to get our terminal side. In example C, this is an application of bearing using method 1, where you're just given a single degree measure. Radar stations A and B are on an east-west line 3.7 kilometers apart. Station A detects a plane at C on a bearing of 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. Find the distance from A to C. Okay, so we see that radar stations are on an east-west line. Okay, so you can draw just a horizontal line. All right, stations A and B are on this line, and they are 3.7 kilometers apart. Then we need to measure a bearing of 61 degrees from station A. So you can put in your vertical line that represents due north, and then we're going to measure it from station A. We need an angle of 61 degrees, so it would be like this. And again, you're measuring it from your vertical, so 61 degrees. A is like your vertex, so you're going to go like this until you get 61 degrees, like that. So this angle is 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. So now we need an angle, we need a bearing of 331 degrees from station B. So here's station B. I've got a vertical drawn in. This is due north. And from station B is going to be my vertex. I'm going to create my 331 degree angle like this, going around this way. Okay, that would be 180, and then I'm at 270, and then I need to go up about another 60 degrees to get to 331. So it's going to be right through here. So this is, so all of this was an angle of 331 degrees. Okay, so it's super, super important to get your illustrations drawn correctly in these problems. Now the plane, remember the plane was on a bearing of 61 degrees from station A and 331 degrees from station B. So the plane, point C, is where those two angles are intersecting here. So there's point C. We're asked to find the distance from A to C. So we have to find the distance from here to here. So we can call it X. Now, how are we going to get this? We need a little bit more information. We need to fill in whatever we can about these angles that we were given. So here, angle A, the horizontal and the vertical are 90 degrees, and this is 61 degrees. So that will leave me with 29 degrees here. Let me get my black so it'll show it better. What about angle B? We had 331 going all the way around to here, and then what would that leave for this piece? If you do 331 minus, no, let's not do it that way. Let's look at this as a 90 degree angle here. So we know that this and this together are 90 degrees. And also we know that if it had continued all the way around, it would have become 360 degrees. So that means that from here to here would be 360 minus 331. That would be 29 degrees. Just like this one was 29 degrees. And then here you have 61 degrees. These two together would make 90 degrees. So, can we figure out angle C? So we've got 29 degrees plus 61 degrees. Add those. 29 and 61 gives me 90 degrees. Alright, so that means that this one over here is also 90 degrees because they have to add up to 180. So we've got a right angle here at angle C. And I'm going to draw it in darker so we can see our triangle a little better. Now, what are we asked to find in all this? We're looking for this distance from point A to point C. We've got side AB, we have a measure for side AB, and we've got all of our angles. So we have everything we need to find it. Let's say if I start from angle A, 29 degrees, and I've got a measure for my adjacent side. Excuse me, no, I'm sorry. The right angle is here. That's angle C. So this is side C. This is my hypotenuse. And then from angle A, I want to know my adjacent side. So which trig function can I use if I'm working with adjacent and hypotenuse? Adjacent and hypotenuse is cosine. So I need cosine 29 equals adjacent over hypotenuse, x over 3.7. Like that. So multiply both sides by 3.7. You get 3.7 times cosine 29 equals x. What's that give us? That gives me 3.236. And those units, what were they? Kilometers. 3.236 kilometers is our answer there. 3.236 kilometers. With method 2, this is the second method for expressing bearing. We start with a north-south line and use an acute angle to show the direction either east or west from this line. So example 7, we sketch the following bearings. Part A, we want to sketch north 42 degrees east. So start with our north-south line. Alright, if it's north, then you're going to be pointing north, and your vertex is going to be on the other end. And then we're going to need to measure 42 degrees from this, and we need to go in the east direction, so that's going to be going to the right. So 42 degrees east from our north-south line, so like this. 42. In part B, start with the north-south line. Okay, this one says south 31 degrees east, so we need to point south, and then our vertex will be on the opposite end. And we're going to go 31 degrees east. So east would be this way, so 31 degrees east would look like this. Part C, we're going to draw south 40 degrees west. So here's our north-south line. This one was going to point south. Our vertex is on the opposite end, and we're going to go to the west, so we need to go 40 degrees in this direction. Part D, north 52 degrees west. Start with your north-south line. It needs to point to the north. So your vertex will be on the other side, on the bottom, and we'll go make a 52 degree angle to our west, or to the west, like this. Okay, so that's how the second method for expressing bearing will be drawn. For example 8, A ship leaves port and sails on a bearing of north 47 degrees east for 3.5 hours. It then turns and sails on a bearing of south 43 degrees east for 4 hours. If the ship's rate of speed is 22 knots, which is nautical miles per hour, find the distance that the ship is from port. So what's happening here is we've got this ship over here at, this is, we'll call this point A. So this is the port, and it's traveling north 47 degrees east. So we're going to put our vertical in here, and we're going to let it point to the north. And then this is going to be my vertex, and I need to go 47 degrees in the eastward direction. So from this line I want to go measure 47 degrees, so it's going to be about like this. And it goes for 3.5 hours that way. It then turns and sails on a bearing. So up here we're going to say that this is where it turns, and now it's going to sail on a bearing of south 43 degrees east. So we'll put in our vertical. So if we point it to the south, this is going to be our vertex now. And we want to go 43 degrees east from this vertex. So that's going to be like this. And this time it travels for 4 hours. So it was 3.5 hours this way and 4 hours this way. So we'll put that in. 3.5 hours, 4 hours. If the ship's rate of speed is 22 knots, or nautical miles per hour, find the distance that the ship is from port. So the ship is now sitting out here. We'll call this point B. So we need to determine the distance from A to B. So we'll call that our X. Okay? So in order to, now that once you've got the picture drawn, the problem is not difficult to solve. Basically, you see we've got this triangle going on here. We're going to put in our angle measures that we were given and see where that takes us. So we know that the north 47 degrees east, that was this angle, that was 47 degrees. And also we had an angle of 43 degrees, so when the ship turned, so it was south 43 degrees east, so that would be 43 degrees here. Okay, now the trick to this, you do have to know a little bit of basic geometry, and I can't, let me, it's not showing up very well, so this angle is 43 degrees. So the trick here to this is, from thinking back to geometry, notice these two lines that we've drawn in here for our north-south lines. These are going to be parallel lines. And this line coming through here, this 47 degrees east, it touches both of those, and this creates a transversal. And we know from basic geometry that a transversal, or a line that transverses two parallel lines, creates these alternate interior angles which are equal to each other. So this angle here is an alternate interior angle with the 47 degrees. And because these lines are parallel, that means that those two angles have the same measure. So that tells us that this angle here is also 47 degrees. Now that's helpful because we know that this piece over here is 43 degrees. 47 and 43, it makes 90. So this is how we get our right triangle. So we have a 90-degree angle up here now, taking these two little pieces and combining them, getting into this 90-degree angle. Okay, so we have a right triangle. That makes X, this side, our hypotenuse, and there's our 90-degree angle. And then this is angle A, so we could call this side A, and this is angle B, so this is side B. And let's put it there. What else do we need? Alright, in order to determine this distance from here to here, because we've got a right triangle, And also because we have values on these two sides, maybe Pythagorean theorem is going to be our way to go here. The only thing is, do we have the distances from A to this point, which we didn't give a name, but we could call this point C if we wanted to, where the ship turned. Do we have a distance for this side? Well, actually we don't, because it just says 3.5 hours, so that tells us how long they traveled it. Can we find the distance from point A to point C? Well, yeah, we can, because we have the distance formula. Remember, your distance formula states that distance equals rate times time. So our distance is going to be equal to the rate, which they told us was the 22 knots, times the time, 3.5 hours. Multiplying this, so 22 times 3.5, what does that give us? That's giving me 77. So my distance is 77 miles this way. So I'm going to replace that 3.5 hours with the 77 miles, as that's the actual distance. Okay. What about side A? Well, its distance is going to be the rate, which is also 22 knots, times the time, which is 4 hours. 22 times 4 gives me 88. So that means side A has distance 88 miles. Okay, so we have everything we need now to find x. If we use the Pythagorean theorem, side x is our hypotenuse, so we have x squared equals a squared plus b squared, so 88 squared plus 77 squared. So 88 squared plus 77 squared gives me 13,673. Take the square root of both sides. We get x equals I get 116.93 or 117. So we'll say 117 miles. Okay, so that's a bearing problem using the second method, where they give you a north and an east, or a south and an east, or south and a west, etc. The directions. And we are almost done with this section. We've got one more. All right, example 9. Francisco needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. He then moves back 50 feet. From the second point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree to the nearest foot. So I've drawn in all that's going on here. So this is Francisco is first standing right here. Okay, at point A. And his angle, this is his line of sight, his angle of elevation is the 36.7 degrees to the top of the tree. Then he backs up 50 feet, and now his line of sight to the top of the tree is this 22.2 degrees. Alright, we're asked to find the height so here's my tree over here, and the distance from point B to point C is my height. We're asked to find this distance, this measurement here. Okay, so did they say anything about how tall Francisco is? Do we need to account for that? I don't remember. Let me check on that real quick. Yeah, they didn't say anything about his height. So I guess that means he's lying on the ground. Okay, so I guess we can just assume that he's actually lying on the ground when he does his angles of elevation, but that's okay. So, how are we going to how can we find this measurement over here? So let's look at what we have. We know that we can use our trig functions to help us if we're working with a right triangle. We've got these two angles. We can get this angle up here pretty easily, but I don't know if it's actually going to help us. But let's fill in everything that we can think of here. So if this is 180 degrees, and then this piece is 36.7, so I can find this piece just by saying 180 minus 36.7. That's 143.3. I'm not sure if we'll actually use this or not, but I'll write it down. And then we can find this angle up here pretty easily because it's going to be 180 minus this minus this. So what is that going to give us? 180 minus 22.2 minus 143.3. And that gives me 14.5 for this little angle up here. Not sure if I'm going to use that, but at least that's some information that we have. So we're asked to find the height, and we've got these two different triangles to work with. So let's think about how we could express height for each triangle. Let's look at the smaller triangle first. We've got this angle 36.7, and we've got height is the opposite side. And do we have anything for, do we have any values here that we can put in? Well, that's okay, we can use x. So if we look at our small triangle, we can see that if we look at from this angle of 36.7 degrees, h is going to be our opposite side and x is going to be our adjacent side. So if we think in terms of opposite over adjacent, that would be tangent. So we can say that tan of 36.7 equals opposite, which is h, over adjacent, which is x. We can do the same thing with the larger triangle. We know that tangent of this angle, 22.2, is equal to, so now I'm looking at the large triangle. Tan of 22.2 is going to be opposite, so h over this side. Now how are we going to describe that long side? It's going to be x, and then there's another 50 feet here that we have to include. So we can say that this is for the small triangle, and this is for the large triangle. We can say that tan 22.2 equals h, which is opposite, over adjacent, which is going to be x plus 50. Okay, so I want to kind of pause there for a moment and make sure that you're clear on how I've done that. I looked at it as two separate triangles. When I look at the small triangle, I can do tan of 36.7 equals opposite over adjacent. So tan 36.7 equals h over x. Then when I look at my large triangle this way, I'll do tan of 22.2 equals opposite, which is h, over adjacent, which is x plus 50 for this piece from here to here, because that's where he backed up 50 feet. Okay, so we've got these two separate equations. What if we solve each of these for h, because they both have the same height, whatever the height of that tree is. We can solve each of these for h, and then we can substitute one into the other in order to solve for x. So over here, I'm going to multiply both sides by x. That'll be x times tan 36.7 equals h. For my larger triangle, I'm going to multiply both sides by x plus 50. So I'm going to have parentheses x plus 50 times tan 22.2 equals h. Okay, so I have two different ways to express the same height of the tree. The height is x times tan of 36.7. The height is also x plus 50 times tan of 22.2. So let's set these equal to each other because they're both the same height. So we have x times tan 36.7 equals x plus 50 times tan of 22.2. Now we can solve this for x, and once we solve it for x, we should be able to solve for h pretty easily. So to solve this for x, we need to get all the x's together on the same side of the equation. So I'm going to distribute this x and this 50, I'm going to distribute my tan 22.2 inside the x plus 50. So that gives me x times tan 36.7 equals x times tan 22.2 plus 50 times tan 22.2. And then I subtract this term on both sides. This might remind you of something that you did in 171. It's kind of like when you had to solve logarithms. That's what it makes me think of. Anyway, subtract x times tan 22.2 on both sides. So you've got x times tan 36.7 minus x times tan 22.2 equals 50 times tan 22.2. Alright, and then over here we can factor out our x. X is our common factor. So we have x times tan 36.7 minus tan 22.2 equals 50 times tan 22.2. Sorry. Yeah, that's what I've got so far. So I've factored out my x on the left, and now I'm ready to divide both sides by this tan 36.7 minus tan 22.2. So that gives me x equals 50 times tan 22.2 over tan 36.7 minus tan 22.2. And be careful when you type this into your calculator, make sure you put all of this in parentheses. And you're also going to need parentheses around the inside of the tan function. So you're going to have two sets of parentheses in your denominator. And now we're ready to type all this in. So I'm going to let it sit there for a moment in case you need to go back and look at anything, because it is a lot. Okay, so let's type this into the calculator. I'm going to put parentheses around my numerator also, because if I don't, my calculator might screw up my order of operations. So just to be on the safe side, I'm going to set parentheses 50 times tan 22.2 close parentheses divided by open parentheses tan, and then the calculator is going to open parentheses for you here. So put in 36.7. Close those parentheses, and then subtract tan 22.2, close parentheses twice now. All that gives us 60.49675. Alright, so we got 60.4967520. So I'm going to round it to 60.5. So I've got x equals 60.5, okay, but I can't stop yet, because remember, we're asked to find the height, h, and we have x, so we're almost there. We just need to put x back into one of our equations at the beginning. So let's put 60.5 back in, and I'll put it in here for this x. I'll put 60.5 there. So that'll give me 60.5. Or as a matter, no, I'm actually going to just use the same answer for my calculator. I'm going to go second enter, so I don't have to retype it all. Oops, I don't want to do that. I'm sorry. I'm going to go second answer, which is the second answer times tan 36.7. Close parentheses. And that gives me 45.0928. So we can say that's about 45. So our height is, and I apologize, I'm completely out of room. So here at the very bottom, I'll say h equals 45, and I believe it's in feet. 45 feet. Okay, so there's a lot going on in that problem. It's just a lot of algebra there, but I don't think it's that bad. It's just got a lot of algebra to it. Okay, and that concludes section 5.4. It also concludes chapter 5. So we've got 2 more sections to cover before we end this module. We're going to cover 6.1 and 6.2, and then we will be ready to bring module 1 to a close. Alright, so I'm going to stop there. Thank you, and we will work on this more together in class.